afternoon, everyone. I'm very happy to welcome our today's speaker, Professor Krishna from Ashoka University. Before starting with this talk, I would like to request you all to keep your audio on mute, and there will be a answer session at the end. Nevertheless, if you want to ask any question or have any comments, so please use the chat box and wait for a signal from our coordinator, Dr. Isan Patri, before unmuting your audio. So welcome, Professor Madali, and I request you to start.
Okay, thank you very much. Thanks for the invitation. I have been working on a problem for a very long time. So one gets sometimes sidetracked, sometimes makes a little progress and so on. So this is one of the problems that me and my collaborator, Professor Werner Kirsch, in Germany at the University of Hagen, landed with when we were thinking about that question. Both of us were thinking about it for a long time, as do many others in the world. So I'm going to tell you about what is quantum lattice waveguide and what is the problem I was working on and so on and so forth as we go along. So in quantum mechanics, it was observed that objects behave both like a wave and a particle. So something like a wave and a particle, and there is no connection because normally we would expect the wave for it to exist, it should exist in something else, whereas a particle can exist by itself. That is the perception that we had. But it was found that some features of quantum mechanical objects exhibited both these properties. So then the question of describing them mathematically arose. So here is the problem. The problem is the time evolution of the objects that are particles are described by Newton's laws. Namely, if you look at the acceleration times mass, that should come from the force that acts on the particle. So that is the classical Newtonian law, subjecting particles to this behavior. Whereas for a wave, the time evolution is given by a wave equation. The second derivative of the amplitude of the wave satisfies this second order equation with possibly a source term. That means if you, for example, in water, if you put a stick and keep moving it, that will generate, the wave will be subjected to this with that movement, which is the source. So that can change with time and position. So both these are one-dimensional objects, one space and one time. So this is the description of a wave, and this is the description of a particle, its time evolution as we understand it. So for both the particles and waves, the configuration space is supposed to be positions of the place where you're measuring it. So that's why the x, that can change with time. Now, when in quantum mechanics, it was observed that a quantum object has both these features, then one had to understand what is the equation that such an object satisfies. So Edwin Schrödinger gave an equation that describes such objects after reinterpreting the wave aspect of the quantum particle. And so what he did was he took some function of x and t. X is still the non-space dimension, and t is one variable. So this equation turns out to be a linear equation in t, the first order derivative. And on the right-hand side, you have a linear operator acting on this function, a second derivative as it appeared in the wave case, and some force term, where the force, like the Newtonian particle case, comes from a potential given by the negative of the derivative of the potential, that is the force. So this is the source kind of a term. And this is the free term, and the time evolution of the amplitude of the wave associated with the quantum object is described by this equation called the Schrodinger equation. So here the function psi is interpreted as the function that gives the probability of finding the quantum object in a region of space. Psi itself doesn't give the probability, but this integral computed over the region of space S, the probability of finding the object in this region S is when the state is psi, is modulus of psi x t square dx over S. So that is the probability of finding it. So somehow the wave nature is reinterpreted as a statistical behavior of the particle. So that's a kind of interpretation, meaning that you cannot find the particle precisely, but if you look at the region of space, you can find it with some probability, and that amplitude is the psi, and the mod square over the region S is the probability of finding it there. That's an interpretation that is given for the wave and particle nature of the particle. So this leads to modifying the Newtonian model for particles which has state space. The position and momentum are the two coordinates that fully describe a particle's position, state at any given time t, the position and momentum. So the state spaces are two. If you are looking at one dimensional case. And this model is modified to the Schrodinger model, where the state space, namely these functions, come from a Hilbert space, namely all square integrable functions on our square integral with respect to the Lebesgue measure. So this is the state space that one considers. So a point here is a state psi, in contrast to a point in xp in R2 being a state for a classical particle. So here, while we have associated a state, unlike the classical case where a point in the state itself gives you position and momentum, that is the one that parameterizes a state there. Here, because it's a cloud that parameterizes, you need to find out a different way of knowing what is the position of this quantum object and what is its momentum. So in this case, it is the two linear operators, linear self-adjoint operators, namely Q and minus I d by dx. These are the two linear operators on this state space that give you the analog of position and momentum. Because these are linear operators, you need to interpret it in a certain way. So in d dimensions, for example, the state space is L2 of Rd with respect to the Lebesgue measure. And the Schrodinger equation becomes the time derivative factor is the same, but the operator that acts on the state is modified to the Laplacian, the second derivative on each of the coordinates, and the potential function also changes. And this linear operator on the right-hand side that appears, namely h is equal to minus d square by dx square plus v, where v is interpreted as an operator of multiplication by this function acting on L2 of Rd. So such a linear operator is the one which is the analog of the energy operator of the classical case. In the classical case, the energy is given by x squared plus p squared in some cases, or p plus, if there is a force, you have p squared plus v in the classical case when you have potential energy. So similarly, here the p is replaced by id by dx, so p squared is replaced by this quantity, and so that is the analog of the momentum. First, the analog of the free energy, and then a potential you have, and this is the quantum mechanical body for which the time evolution is generated by this Hamiltonian H. So the time evolution of the state is given by a linear self-adjoint operator acting on this. Typically, the operator H above is self-adjoint and its spectrum is of interest because it gives you the possible energies of the system. From the Schrodinger equation, we also see that if E is an eigenvalue of the operator H, then the time evolved state looks like psi is EI e to the power IET times psi of x0, because in this equation, if this whole thing acting on this gives you a number, then the derivative solution is exactly this, because it's a linear operator. So that shows that if you start in a region S at some time 0, and if the probability is something mod psi square integral over S, then as t varies, it doesn't change because the modulus of this factor that depends on time is 1. Therefore, for such states, namely the eigenstates of the Hamiltonian H, the operator H, the probability does not change with time. So such states are said to be bound because it doesn't change. And therefore, the states, for a state to have different probabilities to be found in the region S as time varies, they have to come from the continuous part of the spectrum of this self-adjoint operator H. It cannot come from the eigenvalues of H. One says that the continuous spectrum is associated with transport of the quantum object because it can possibly move the object from a given region as time varies. So thus, the spectral theory of the operator H becomes important to understand the dynamics of the quantum object. So they are intimately tied. Physicist's intuition is that energy drives the dynamics, and that is why this operator drives the dynamics. In other words, if you don't have energy, you cannot move. So up to now, the discussion is about one quantum object subjected to some force coming from a potential V, such as a nucleus and an electron there in free space. So the nucleus gives you the V, the potential, and the quantum object is an electron, and that is moving around, and that is subjected to the Schrodinger equation, and everything is fine. You have state space and so on for the electron and all that. So all this description of the Schrodinger equation is just for one quantum object moving in some kind of a force field. What if there are lots of atoms and lots of electrons moving around? What happens then? So what about the case of lots of electrons moving in material like a slab of iron or a piece of glass and so on? So such material will consist of atoms located, and the atoms are not going to sit on top of each other. There is some space between different atoms. So a solid material consists of a set of atoms sitting in a position of a lattice of a certain structure. It could be any structure. I'm just taking the lattice to be ZD, for example. So atoms are located at the lattice points of ZD, and the object could also be, it cannot be absolutely pure. So let us see that later. So anyway, if you have an object like that, like a slab of iron, lots of electrons moving around, then how do we describe it? So for such a system, P.W. Anderson gave an approximation of the Schrodinger equation, where the Hilbert space of states is given by little L2 of ZD. ZD is the space in which at each lattice point there is an atom sitting there, and square summable sequences on this space is the state space, and the energy operators are given by H is equal to this quantity that replaces the free part of the energy and a potential. So because ZD is just a lattice, any vector delta n that is sitting at the site indexed by n, which is 1 there. So take a sequence which is 1 at the site n and 0 elsewhere, that you call that as delta n, those vectors. This object determines the orthogonal projection onto such a unit vector in L2 of ZD. And then you take a sequence of numbers Vn, real value sequence, and this represents a diagonal operator, which is diagonal in that orthonormal basis formed by the unit vector supported at the point n. Okay, that forms an orthonormal basis. So this part of the operator is just a diagonal operator with a real diagonal. And this operator is just, if you take dimension to be 1, this is just a shift by 1 in the jth direction, either to the, it's a bilateral shift. So you shift to the positive side, let us say, and then it's inverse, which will shift you backwards. So together, they form a self-adjoint operator because of the form U plus U star. So if you look at it as a matrix in one dimension, this is nothing but a matrix with ones on the off super and subdiagonal and 0 everywhere else. So in one dimension, this Hamiltonian is nothing but a tri-diagonal matrix with real diagonal entries and a sub and super diagonals are 1. So that is the energy operator that Anderson proposed for one dimension. And similarly, you can extend it to d dimensions by taking the bilateral shift in the jth direction, and it's adjoint. And adjoint and inverse are the same because they're unitaries. So we take this is the analog of the free energy part, and this is the potential energy. So this is the model that describes the configuration that is a quantum object is subjected to when it is moving in a lattice. So this is the model. Since any material has impurities whose location is impossible to determine, one takes a parameterized family of the above type of operators to study such disordered systems where the function could vary. See, for a given material, if the atoms are all identical, then the V would be the same because they all exert the same force. But if one atom changes to some other material, some impurity, then the V changes. So to study a property of such an object, it is really impossible to say what atom is where. So one has to consider a family of these things by allowing for possible values of Vn. And that's why this is no longer one operator, but an operator parameterized by something that will correspond to changing V at different places. So in other words, if you fix one sequence Vn, that corresponds to one configuration of atoms. If you change it, it can correspond to another configuration of atoms and so on. So this leads us to a random self-adjoint operator called the Anderson model. Excuse me. So the Anderson model, to describe it, we take a probability space omega BP and a family of multiplication operators V omega on L2 of ZD, real valued random variables on omega. We then consider V omega of n is a real valued random variable when n is in ZD, and this is just operator there, multiplication by them. We then consider the operators of the previous slide denoting H omega to be the delta, which is the first part, and delta is this part, and V omega is the diagonal part. So when there is an action of ZD on the space omega, and the corresponding action of ZD on itself by induced unitaries on L2 of ZD, if you denote the action of ZD on L2 of ZD by induced action, then we require that this collection of operators satisfy H of S omega. S omega is S is acting on omega and U is acting on L2. This is a unitary. This action gives you an operator that is unitarily equivalent. So this property is called homogeneity. In other words, if you look at the material differently from a different perspective, the physics should not change. And that is a requirement that you must have this covariance and what is called homogeneity in physics literature, covariance in the mathematical language. So we require this covariance with respect to the action of ZD on omega and L2 of ZD. And once you take this model, then it is a theorem of Pasteur that such covariance assures the constancy of the spectra and the spectral components of this family, H omega, which means a priori this is a self-adjoint operator that depends on omega, this parameter. So its spectrum also will change with omega. But this covariance assures us that the spectrum is a constant set. And it's not only the spectrum, but spectral component, namely the point spectrum, absolutely continuous spectrum, and such components are all constant sets. So let me depict the potential by some arrows. So here are some arrows. The potential here is large, the potential here is small, negative, positive, and so on. So to depict the size of the potential, one puts a parameter lambda that denotes the size. So when lambda times u omega n are ID random variables distributed with respect to summation mu, then the spectrum of this h omega, which is a constant set, is this fixed set for almost every omega. Okay. So the theorem of positive assures you only a probabilistic constancy in the probabilistic sense, in the measure theoretic sense, in the sense that this is a constant set for almost every omega. So this is the fixed set, which is the spectrum of almost every operator. So there are two features for this spectrum. First, there is a pure point component for lambda large called large disorder regime in any dimension. It is expected that there is some absolutely continuous spectrum for small disorder lambda small, called the small disorder regime. Now, mathematically, it is shown that for this class of operators, when lambda is large, that this entire set has only point spectrum, which means that there is no continuous spectrum in this entire spectrum, if lambda is sufficiently large. So that part is shown. And the second part, where in one dimension also this is the case, that there is no continuous spectrum in one dimension. Whereas if you change the dimension to 2 or more, then it's a conjecture that when lambda is small, there is a part of the spectrum which is absolutely continuous. And that is a major open problem in this subject, and no one has any clue. And it is this problem that we were interested in and we were addressing. So what we looked at was what is called a trimmed Anderson model. The attempt is to understand this conjecture coming from the for the Anderson model, for the trimmed Anderson model, namely, you assume that there are some atoms missing at some sites. So you have this lattice of atoms, assume that some sites are missing, some atoms have disappeared. Then you will have a subset gamma of ZD where the potential is present, and in the complement of gamma, there is no potential. So that is what is called a trimmed Anderson model, which is what we were looking at. Because we have no idea of what to look for the full model, we thought we would look at this. There were some attempts to understand this model. So in attempting to address this question of absolutely continuous spectrum for the Anderson model, we ended up looking at the quantum lattice waveguides. So this is nothing but the Anderson model on a Hilbert space like. You take L2 of split ZD, the d-dimensional lattice, into two parts. One part is a d1 dimensional lattice, partition product with a finite set raised to d2. So this is like a tube. Okay. So this configuration, if I take d1 to be 1 and d2 to be 1, then this is nothing but there are m lines. Right, M lattice lines. So that is that's a quantum lattice waveguide. Classical waveguide is nothing but you just take a rectangular three-dimensional tube, which is hollow here, and that's a quantum waveguide. The classical waveguide. The point of a waveguide is that if somebody is sitting here and somebody is sitting here and shouts, then the voice goes like a spherical wave. So for somebody sitting somewhere here, the wave, only a part of the wave can be heard. So most of the wave is lost. So most of the sound is lost. For example, if you're shouting from here at somebody, somebody is sitting here and you're shouting from here, most of the sound is lost when you reach that person. Whereas if you use a waveguide and shout from here, then not much is lost, and waveguide can carry the sound much, much further distances, orders of magnitude different. And that is why waveguides are important for carrying a wave without much attenuation. So that's what is a classical waveguide used for. So we were looking at the analog of that, which is a quantum waveguide. So waveguides are useful for reducing the attenuation of a signal. So we consider the trimmed Anderson model on quantum lattice waveguides, namely, we look at this model where gamma is a subset of the lattice on the Hilbert space, which is Z of D1, and then some finite, in some directions, the number of atoms are finitely many in that direction, raised to D2. So gamma is a subset of this. So our trimmed Anderson model looks something like this. So for example, it could be missing at the brown sites, the potential is zero at brown sites, and at the green sites, it could be present, and the green and red denote different types of atoms. Okay, so this is some configuration that is possible. So at the brown sites, there is no potential. Gamma is simply this, where you have green and red. So that the potential is zero on brown, and it is present somewhere here. So to mention the theorems, typically to indicate disorder, one takes this coupling constant lambda that I wrote down. When lambda is large, you say large disorder. The reason is that when the potential V at a point is, say, 1, then for a large lambda, this will be very large. If the value of the potential is, say, 1 over lambda, then the value of lambda times V would be 1. And similarly for positive and negative. So this just blows up the size of the potential at a point. So typically the intuition behind the reason why for large lambda you only have point spectrum is because if you think of this as the two-dimensional lattice on which, for the moment forget gamma and gamma complement, suppose this is the lattice on which the potential is present everywhere and lambda is large, the potential could be positive and negative because of the different type of atoms. So somewhere you may have a large spike here and something smaller. So a particle, when it is moving here, it keeps getting reflected. So gets scattered multiply many times. So when you have very high disorder, that is from point to point, the variation is very large of the potential, then something that is moving here gets bumped back, forth, and so on. It gets scattered like this, and it can never escape. So that is the reason why you expect for large disorder for you to have only bound states. Remember, at the beginning I said bound is equal to the point spectrum corresponds to bound states. So the particle cannot, the quantum object cannot escape. Whereas if the heights are very small, when lambda is very small, then it can slowly tunnel through and escape to infinity. That is why then the states that are there can reach farther away. So that is the intuition behind why for small lambda you have some kind of continuous spectrum, there is transport, whereas for large lambda there is no transport. That is the intuition. So here for the next rest of the talk, so let me consider a two-dimensional lattice, and I'm going to look at gamma to be this, where there are colored dots, and the brown dots are gamma complement. So gamma complement does not support V, so V is 0 on these lines, and V is non-zero here. It could have different values based on the colors. Okay, so I'm going to look at this operator on L2 of minus Z to 2m minus 1 minus 2m minus 1 to 2m plus 1. This is not 2-point set. It's an interval. It's a minus 2m minus 1 minus 2m and so on up to 2m plus 1. So the width is 4m plus 2 of this 4m plus 2 plus 1 of this lattice. So here is our first theorem, and the theorem is the following. for the lattice waveguide. So let gamma be this set, as I wrote down earlier. One direction it is Z, and the other direction it's a finite set. Consider the operators H lambda, gamma, omega on this, with mu having bounded density. H lambda omega is just this operator, okay? And let me assume that the omega n varies with respect to, is in the support of a measure mu. Remember that we are taking omega n's to be in probability space omega. So that has a product measure, product times mu. So mu has support from -1 to 1. So that at every point, v omega of n varies in -1 to 1 as omega varies. To write down the spectrum of this operator, surprisingly, we need to look at two different operators, namely, somehow in some sense, omega being maximal and omega being minimal. So look at this operator where lambda times 1 here, 1 corresponds to this 1, constantly 1. So this operator, you call it plus, and for minus, you call it minus. Because the support of mu is between -1 and 1, somehow if you set all the v omega of n's to be -1, you get the minus operator. If you set it to be 1, you get a plus operator. So consider these two operators associated with lambda and this on this. Then this number E minus, which is the infimum of this spectrum of this self-adjoint operator, and E plus is the supremum of this self-adjoint operator. If you consider, then the spectrum of these, which by the way is a constant set, is between E minus and E plus. You may wonder that there is no ergodicity here. So you may ask me, how are you telling me that this is a constant set? Well, while ergodicity was used by Pasteur proof, there are lots of situations where you can actually show by using the same principles that even when you do not have ergodicity in some directions, you still have a similar kind of result, which is a fact. So for almost every omega, the spectrum of these operators is E minus and E plus, where E minus is the infimum of the spectrum of this, E plus is the infimum of the spectrum of that. So for this model, for this set of operators, the spectrum is this set. The next statement is there is a lambda 0 positive, such that if lambda is bigger than lambda 0, this is the large disorder, lambda 0 would be large. It says there is a lambda 0, so lambda 0 would be large. So when lambda is bigger than that, then the continuous spectrum outside -2 to 2 is empty for almost every omega. A theorem corresponding to, if I replace this by just Z and gamma by the identity, gamma by Z2, then the corresponding spectrum would be that this spectrum is empty if lambda is large. There is no continuous spectrum at all. A large disorder, when you take is the Z times this, you take Z2 and you take gamma to be Z2. If you take that, the large disorder, this is only point spectrum or no continuous spectrum. Whereas because of gamma that we have introduced, because it's a lattice waveguide, you have point spectrum outside an interval. Okay, so that is a fact. So in other words, we will qualitatively describe this. And then the third statement of the theorem is that for any lambda positive and omega, so for any pair lambda and omega, we have the absolutely continuous spectrum of this is equal to -2. So in other words, in this interval, you have absolutely continuous spectrum for this waveguide model. And outside, for large disorder, you don't have it. For small disorder, we cannot say anything there. Okay? So in other words, for large disorder, what you have is this blue is the absolutely continuous spectrum. It may have other spectrum also, but we just showed that there is absolutely continuous spectrum. And then from E minus to -2 and then 2 to E plus, You only have a few point spectrum, no continuous spectrum here for large lambda. So what does this mean for a waveguide? Remember, the classical waveguide is like a tube. If you speak, it will just go without attenuation. So in this case, in this quantum waveguide, so pictorially it says this lattice waveguide with a high random potential, the transmission of, so suppose you're transmitting electricity, say a bunch of electrons are moving in this, such a lattice waveguide, then up to some energy, there is no transmission, even though you're pumping in energy. Even though you're increasing the voltage, there is no transmission. And then at some stage, it starts transmitting, and again it stops. Okay? So this lattice waveguide itself acts like some kind of a filter for transmission. This is remarkable. At least I'm not aware of any such thing in the. There are theoretically there are a few eigenvalues and so on, but because of the randomness and the kind of structure we have here, the waveguide acts like some kind of a filter for transmission. So this itself should give very interesting things later on, which I'm trying to explore. So the interesting part here is that the classical waveguides, there is always transmission of whatever is sent. But here, because of quantization, there is also insulation and the energy is pumped in, right? So we also analyze this case where M is infinite, that is L1 of Z2. And in the Trimmed-Anderson model, we find that for large disorder, something happens. So I'll come to that. I will state the theorem next. So as for the proofs that there is a point spectrum, what one does is to show that there is only point spectrum, one looks at the resolvent kernel of this operator. I have these operators H, lambda, omega. This is gamma, and an epsilon is positive. This is a complex number. And because this is a self-adjoint operator, a complex number is not in the spectrum. It's in the resolvent. So H minus that complex number, that linear operator is invertible. So the inverse is a bounded linear operator. And that inverse, you look at the matrix elements, because L2 of Z or Z2 is just it has an orthonormal basis. You just look in that orthonormal basis the matrix entries of this bounded linear operator. So as y varies, this is a function. Fix S is a function as y varies. It also depends on omega. So if you take the absolute value and raise it to power S for some S smaller than 1, and you take the moment, this moment, small moment, namely the expectation of this random variable, that's going to depend on epsilon and E. So now you take the sup over epsilon. Normally, without taking this expectation, this is a self-adjoint operator. If you take sup over epsilon here, if E is an eigenvalue of this operator, you get infinity, right? The supremum is not going to be finite if E is an eigenvalue of this operator. But because you are averaging some small moment, it turns out that that quantity is finite. Not only is it finite, but with respect to the distance between x and y, it decays exponentially fast, gamma positive. So the small moment of this decays fast, and one can prove this when lambda is very large. The proof is a little, it's not trivial for me to say, but that was one of the major breakthroughs in this theory. Then for lambda large, there are two different proofs. This proof was a little more transparent. It was proved by Michael Eisenman and Stanislav Molchanov. These are the two people who showed this small moment proof that for large lambda, this is small. So when this inequality holds, when S is smaller than 1, and it holds for all E in an interval, then from here it follows that if I look at the matrix elements without taking any expectation, that is for omega fixed, take omega, and just look at these matrix entries and take the square, then that object decays fast enough when you add over y, sum over y. So that is summable. And not only that, this decays extremely fast for almost every omega and e. Here, omega is averaged over, and this statement is valid for all e in an interval. Whereas here, from this statement, you can conclude that this sum is finite for almost every omega e. And this statement is the one that shows that there is no continuous spectrum in that interval I, almost every omega. This was the theorem of Simon and Wolf, who showed that this spectrum is pure point. This criterion gives pure point spectrum. They actually showed that for gamma s, with gamma s 0, that as long as this is L2, then the spectral measure of the operator H omega associated with the vector delta x, that spectral measure is a pure point. There is no continuous part of it. And this being valid for every x, this shows that there is no continuous spectrum. So to show the absolutely continuous spectrum in this region, -2 to 2, we notice that if you look at these functions, psi of x1, x2, given by it's the ik x1 and sine pi by 2 x2, where k is some fixed positive real number, then these are solutions. I should have put a dependence k here, but I didn't do it. So as k varies, look at this collection of functions. That's why I said functions here. So when you look at this collection of functions, then this operator acting on that function, x here is a two-variable vector. So this is delta psi, which is equal to 2 times cosine x times this, times there is a psi of x here missing. I should write psi of x here. There is an eigenvalue equation. And the reason for that is that the gamma we have chosen to be so we will choose our gamma in such a way that gamma times the indicator function of gamma times psi is 0. So psi has support away from gamma. So on this space, delta is given by delta 1 plus I delta 2. So let me go back a little bit and mention what is happening here. I think so I wrote down the set gamma somewhere here. Yeah, my gamma was this set. If you remember, gamma is z times in this direction where you have a Cartesian product of the finite set. There, it is all those points which are even numbers. So in other words, this is a union of lattices, union of z, where this coordinate is an even number. So that is the lattice I've taken. So because of that, what happens here is this function x2 is varying in -2m minus 1 to 2m minus 1. So when x2 is even, it is sine pi, right? So sine pi is 0. And because of that, when x2 is even, which is where gamma is located, gamma is precisely the set where x2 is even in that set. So gamma and psi, the indicator function of gamma acting on psi is 0. And therefore, in this potential, in here, since this potential is supported on gamma, this term is 0 when it acts on this function psi. So V acting on psi is 0 because of this reason. Therefore, the whole operator acting on psi, which is of this type, is precisely delta acting here. And that gives you, if you take this function for the first part, namely the shift x1 plus negative shift of x1, if you take this, that is nothing but 2 cosine x multiplying this function. And for this part, it is 2 cosine pi by 2, and that is 0. And therefore, the whole thing is 2 cosine k acting on this function psi. So the operator acting on psi is 2 cosine kx times psi. And therefore, since k is varying and is any real number, you see that these are just eigenfunctions. And they are not L2 because this function is not in L2 or L1 or anything in Z cross the finite set. So the delta on this interval, because of this reason, breaks up into two pieces, delta 1, which is the first part, and delta 2, which is acting on here. This is just a tridiagonal matrix here. This is the tridiagonal matrix here of diagonals 1s and diagonal 0. This is just the tridiagonal, delta 2 is the tridiagonal matrix here of diagonals 1 and diagonal 0. And this is nothing but the sum of these two matrices with the appropriate identities. So therefore, this function is an eigenfunction of delta 2 because it's a finite matrix. And this is a L2 vector as x2 varies in this set. So this solution is in L2. Therefore, delta 2 has an eigenvalue, which is 0, with an eigenfunction, which is in L2. And because this vanishes on complement on gamma, the orthogonal projection P0 onto this subspace of this vector spanned by this here, tensor identity, commutes with this operator. So if P0 is the orthogonal projection onto the eigenfunction of this matrix corresponding to eigenvalue 0 on this component, then that projection times identity actually commutes with this whole operator. And because it commutes with the whole operator, it reduces it. Therefore, this acting on this is precisely this quantity. And the spectrum of this sum, this object is nothing but 0 tensor identity. And this is nothing but identity tensor delta 1. This is the operator of multiplication by 2 times cosine k. And because it's an operator of multiplication by that, it has absolutely continuous spectrum, which is -2 to 2. So this operator turns out to have absolutely continuous spectrum. And that proves the second, the final assertion that absolutely continuous spectrum is here. So this is how we ended up proving this, while this was not transparent at all, because if you look at the Anderson model, such structures are not clear at all. But somehow, when we were looking at certain trimmed model, it just turned out that we had to struggle a lot actually to prove this trivial thing, because the trivial ring is not transparent. When I write it to you like this, it looks like a trivial statement. But to arrive at this triviality, it took a little while for us. So it shows that there is absolutely continuous spectrum in the waveguide. So the waveguides themselves, the lattice waveguides themselves, quantum lattice waveguides, themselves are very interesting. I think there are lots of applications that are possible on this theorem on waveguides. I can't say anything now, but we'll probably in the future something I can say. But the more interesting theorem for us mathematically is not this, what I said just now, but something else. Namely, it is a theorem on this, on full L2 of Z2. That is a full trimmed Anderson model, where if for small disorder, if we can prove something, that will be great, right? Because it's 2 dimensions and more. So that is the trimmed model we considered. Therefore, we consider this model here on L2 of Z2. My gamma is one direction is Z, the other direction is even coordinates of Z. So with, as usual, mu having bounded density with compact support, then take these operators. As usual, you have this spectrum for the maximum and minimum operator, minimum eigenvalues of this. And point spectrum also is similar. There's a lambda 0 positive such that for large disorder, the continuous spectrum outside this is empty. That's also it's not a great thing. But of course, even this theorem itself, not it was not clear at all. Even several people could prove only that this statement is valid very far away from this set, not even close to this, because of technical reasons. But our proof, we managed to show that just outside for large disorder, you have it. So in other words, it comes very close to this interval -2 to 2. That itself is an interesting part. But to us, the most interesting part is the last part, which says for any lambda positive, if I look at this integral kernel, the resolvent kernel that we looked at earlier, remember this was in L2 when we had point spectrum almost every omega. But here we show that for almost every omega E, when omega is varying in omega, and the energy is in this interval -2 to 2, this integral, this resolvent kernel is not L1. Supremum over eta, when you take, this integral kernel is not L1. Remember, this was L2 and exponentially decaying in the case for large lambda, which is where the energies were outside here. But here, this is infinite. Such a theorem was not known at all. And in fact, this shows that this is almost the first step towards showing that for small disorder, something is happening here in this region where you expect absolutely continuous spectrum. We could show absolutely continuous spectrum in this energy region for quantum waveguides, quantum lattice waveguides, namely this Z is reduced to a finite set. But when you take a full L2, we can show this statement. That itself is a remarkable progress for us. That's what is here. The reason this is interesting is, for the first time, we could show that the exponential decay of the resolvent kernel is not possible in a part of the spectrum for a class of ergodic operators. Our theorem is the closest anyone got, showing that the high dimensional ergodic random operators, there is a phase transition as energy varies. So we call that a phase transition. The proof of this statement again proceeds similar to the previous one, for which what we have to do is we take the full operator, cut it off into a finite box of size L, take a square of side length 12 plus 1, cut off the operator into that, namely take a finite dimensional matrix. You have these solutions, approximate them, and did anyone ask a question? Was there a question? So what we do is, this equation is just an eigenvalue equation. Namely, you write the resolvent times this operator, the product is just identity. So if I take the identity here and split it as two pieces, the inverse and the identity, and write it down, what we have is a equation like this. For that solution, for this solution, psi1, psi2, that satisfies this eigenvalue equation. Psi is this function, okay? We get a term that lives on the boundary of the square of side length L, and a term that there's a factor of eta here. Same eta is the imaginary part of this point appearing in the resolvent equation. So you have a sum of these quantities. Now we have here a bounded function, and therefore, and the function on the left-hand side has modulus 1. So if I take a modulus here and get the inequality, if we assume that this quantity is in L1, then because this is L1 in the whole space, if you take it on the boundary of a square and as L goes to infinity, this term goes to 0. And what is remaining is this. So for every eta positive as L goes to infinity, this term goes to 0. This is actually a dependence on L here. You have to take a projection onto L. That converges to the identity, so this is only 1. And on the right-hand side, this goes to 0, and then you have a term with eta times L1 norm of this. When you let eta go to 0, that term also vanishes. So the right-hand side vanishes as eta goes to 0, as L goes to infinity, whereas the left-hand side is 1 for certain points x1 and x2. What are those points? Those are the points where x2 is in 2z2, 2z, and x1 is in z. This statement should be x1, x2 is in z times 2z. So for all those points, you get a contradiction. So for all those points, x1, x2, says that x1 is in z and x2 is here, you show that this sequence cannot be in L1, and that is this thing. I should have said that the x should be such that x is in this set. So if an x is in gamma, this is in. So that is the most interesting theorem for us. Thank you.
Any questions?
Yeah, I have a few questions.
Yeah.
So I mean, I apologize if they are not probably might be a bit stupid. So first, so this structure of this operator that you wrote down, even in the first instance, the bilateral shift part and potential part. Now,
Yeah.
is it coming from some kind of intuition that the dynamics is driven by the free energy, so that the movement is only possible from the bilateral shift, while the other part is simply keeping every vector constant, something like that?
No, it's not. It's not like that. It's like potential energy and kinetic energy. In this case, if you just have potential energy, right? There's no transport, as I said, because the diagonal operator, every state, the basis vectors are in the right. So there's no transport there. It is true that it is the kinetic energy part that gives you the transport. In fact, if you think about it a bit, if you think that the space R is somehow digitized and you have an epsilon, then the definition of a derivative, if you take f of x plus epsilon minus f of x over epsilon, when epsilon is 1, is just nothing but finite difference of one shift.
Yeah.
So second derivative is exactly that. U, if you take function u of n plus 1 plus u of n minus 1 minus 2 times u of n, is precisely the second derivative in this sense. Right? So this is exactly the analog of the derivative part that drives the motion. Right.
I see.
That is correct.
Okay, I see. So second question is that this homogeneity condition that you wrote down, so that was a ZD action on the space. So although it's not relevant to probably the physical origins of the question, but from an ergodic theoretic point of view, has other groups been considered, like let's say amenable groups or more?
One considers, what one does is, you can pose this problem in with respect to some group. For example, you can take a torus on which you have a group action.
Yeah.
So L2 of the torus and pose the problem there, and such things where the random potential comes from a function there. So for example, you take the torus and take an ergodic action there, and then parameterize the random potential using points of the torus. So functions from the torus, taking values in the diagonal matrices on L2 of ZD, real value diagonal matrix on L2 of ZD, that will give you an ergodic system also.
Yes.
Okay, except that there, if you take the entries of the matrices, V omega of n, they won't be independent random variables, they'll be dependent. Okay?
Yeah.
So all this, it's done in great generality actually. I am looking only at this case where at different sites, the random potentials are independent random variables. And that is the Anderson model. Whereas the random operators themselves, the ergodic setting, it is very general. Lots of theorems. I mean, it's a huge subject.
And finally, one this. So when you trim it down, but you are, I mean, this is this point probably at some point you made that you lose the ergodicity, and but I mean,
no, you still have ergodicity with respect to a subgroup.
Yeah,
you don't have it Z2.
Yeah, right, exactly. So
But even that was not known to a subgroup ergodic.
So even that, I see.
Right.
Any more questions?
Proofs seem to be rather easy, trivial, but because of the nature of the problem, and it was also hard to realize that there is such a solution. Until one solution was produced, it wasn't clear at all what was happening.
I see. Thank you, sir.
Yeah.
Yeah, once again, I have a question.
Yeah.
Once again, that operator which Ishan Bhatri was mentioning, Tj plus Tj inverse and this potential part, it looks like a creation and annihilation and a number kind of thing in Fock space. Can you frame these problems in Fock space, boson Fock space?
See, the Fock space is the shift operators are just the shift on either a unilateral shift or a bilateral shift, right? In the case of Fock space, what happens is you're shifting from different spaces of different dimensions.
Mm-hmm.
Here it is just L2 of Z. That's it, nothing else. L2 of Z or ZD. Right? The fact that you can view a shift as a creation or annihilation is irrelevant to this problem. That's an accident.
Okay.
Right?
Okay.
It's not related. That's why, as I said, you have to look at the bilateral shift here and its adjoint, the sum, as a second derivative in a space which has points at a distance 1.
Mm-hmm.
Right? Instead of continuous space R, suppose suddenly R becomes Z.
Mm-hmm.
Then if you apply the definition of derivative to that space,
Yeah.
you will f of x minus f of x plus y minus f of x over y. As y goes to 0, instead of that, you take y going to 1. Because space between points is 1. Distance between them is 1. And that definition of a derivative is a standard definition of a derivative. Gives you this second order method. It's up to your constant.
Okay, thank you.
Yeah.
Any more questions?
No.
So if there is none, we thank Professor Madali for the nice talk. And so maybe we can close this session. Yeah, thanks a lot.